Okay, I had a viewer ask me a question, which at first, when I first read the question, I thought, well, that's a trivial thing. I don't think I need to do a video on that, and then I started thinking about it, and there are no dumb questions. And there's also another saying that says, you'll never really understand something until you teach it. And I began to think of how would I teach this, and it started questioning my own reality. It's like, okay, well, wait a minute, I don't really think I understand that. Even though it seems like it's such a trivial thing, I don't think I actually understand it. And it led me to believe that, yeah, I've been kind of, I don't know, I just never thought about it too much. So anyway, the question is, how do circuits trigger on edges? And how does a microprocessor trigger on an edge? How do circuits use edges? And this came out of a video I did on comparators. A comparator will compare something and it'll create a rising or falling edge when some event occurs. And you have this edge. And then you say, okay, well, what are you going to do with that edge, right? And so one of the first things I ever learned was D flip-flops. They were the first edge-triggered circuit I ever learned when I was a kid. And the basic chip that everybody learns is the 7474. And it's an easy number to remember too, 7474. There's 7400 logic series, but the 7474 was an edge-triggered flip-flop. Well, this is how they're generally drawn. And this little diamond-shaped thing indicates that it's not a logic level. It's not like you have like a NAND gate, right? You have a NAND gate, and you have A, B, and C. The value of C depends on the logic state of A or B. Is A high, or is A low? Is B high, or is B low? That will tell you what C is going to be. But when you see this little chevron thing here, it says, okay, this is no longer a logic state device, it's an edge trigger device. And what it does is whatever value D has, if D is 0, then the next rising edge of clock, the Q will be 0. And if D is 1, the next rising clock will make Q 1. It's like a sample and hold. It doesn't matter what's going on here until you see the rising edge, and then it'll lock in that state. It'll sample that state, and it'll lock it in here. And the not Q is just the inverse of that. And then there's a couple of the signals here we're not going to talk about. There's a preset and a clear. That's kind of like a J flip-flop, JK flip-flop. You can set these things high or low in state, not in clock, but in state. But this is the clock thing. And in these circuits, one of the very, very first things you learn is to do this. Okay? And if you do that, then let's say that not Q is 0. Then the next rising edge, this 0 will make this 0. It'll sample that 0 and it'll make this 0. If this is 0, then this is 1. And then the next time you see a rising edge, this is a 1. And if you clock that, then this becomes a 1. And so it'll count. It'll go 0, 1, 0, 1, 0, 1. And it'll only do so on rising edges, okay? And so that's the way you make a flip-flop counter. All right, so let's look at how this device uses edges, because it's edge triggered. Okay, what does that mean? All right, so I got the data sheet out from Texas Instruments, and I looked at, and this one is a nice data sheet because it has the actual schematic of the part. All right, now this is a bit complicated, and I don't want to go through this whole circuit diagram. But what I want to do is I want to give you the idea of what the circuit is doing. So I'm going to do it in simplistic terms first, and then we'll come back to here and I'll kind of point to things and say this is that thing and this is that thing, and I'll let you study this on your own. But I want you to get across of how this thing handles edges. What does that mean? All right, so let's talk about flip-flops. I always explain flip-flops as a teeter-totter, okay? And if this is the Q output, and this is the not Q output, it will always be the opposite state. If you flip it this way, then Q is 1 and not Q is 0. If you flip it this way, then Q is 0 and not Q is 1. Okay, clip, flip, flip, flip. So that's a flip-flop, okay? Well, if you have a JK flip-flop kind of thing, you're able to pull down on it, okay? You can pull down on it this way, and that sets Q to 0. And you can pull down on it this way, over here, and that pulls Q0 to 0, but it makes this one a 1. So this is your clear. If you pull down on it, it makes Q0, that's a clear. If you pull down on this side, then Q goes up high, and that's a preset. So clear and preset, right? So think of this as a teeter-totter, and you're able to pull on it, okay? But let's imagine that this is an electronic teeter-totter, okay? And the idea of pulling, we're going to have a switch, okay? So we'll have a switch here, and we'll have a switch here, okay? So if we close this switch, we can pull down on it. If we close this switch, we can pull down on this side, okay? And they are state, okay? So this is a switch, and this is a little push button switch. So these are the little buttons on them, and there's springs, okay? And so if I push down on this one, then its state is high, and it'll pull down. And if I push down this one, its state is high, and it'll pull down. Okay, so there's these switches, okay? And these switches would have to go to ground, right? And the top part of the switch, let's say, goes to +5. Okay, so that's the way these work. If they're switched, they're 5 volts. If they're switched, they're ground. If they're unswitched, they're 5 volts. Okay, so that's the way that these switches work, right? You tie them to ground, or you could tie them to +5, right? You could make it so that when you close them, they go high, and when you open them, they go low. Just depends on how the circuitry you want this to be, right? Okay, so this got a bit messy. But we're still going to have switches. Remember the switches, okay? We've got these 2 switches. All right. Now, how do we make this edge triggered? Okay, how do we do that? Well, let's say we tie these together and we put another switch down here. Okay. Now, these switches will not function unless this switch is closed. I could push these all day long and nothing will happen. But if this switch is closed, then these will work. You can call that an enable. Okay, so this is an enable pin on a device. You can enable it, and then you can use the 2 states, right? And so that's the idea. There's going to be a teeter-totter. There's going to be a do I reset or do I clear? Do I preset or do I clear? And there's an enable. Okay. All right. So. Let's see, when do I want to go back to the schematic? All right, so instead of switches, okay, I'm going to have transistors. Okay. So transistors can act as switches. Right? And I could have a switch down here, which is another transistor. Okay. So you can see that, right? So this one will pull down on that side, and this one will pull down on this side, and you can have some transistors over here, and some resistors and stuff, and you can take this one and tie it over here. You can take this one, you can tie it over here. You can cross these 2, and you can make a flip-flop out of transistors. Okay, I'm not going to talk about that, but you can go look it up. And if one is set, it clears the other one. If this one's set, it clears the other one. And so this is a teeter-totter, right? And you can kind of reach in and you can pull down on one of these. So if this one's already pulling it down, fine. But if this one's not pulling it down, you can reach in here and you can pull it down. You can do that with diode switching. You can put in some diodes here, okay? And that diode switching, if you go over here and you ground here, you'll pull that side down. And then the diode will get out of its own way. Once you let up on it, it'll get out of its own way. So this diode switching thing, right? And you could tie these in, and this thing could reset with these guys, and this will be the enable. This will be the enable pin, right? So I hope that's clear. Okay, teeter-totter, set, reset, and some type of enable. Okay. Let's take a look at what we have here. All right, top part. See these X's here? That's the crossover. This is Q. This is not Q, and this is Q. It's fancy, but it is a flip-flop, right? Bunch of transistors over here, a bunch of transistors over here. But either if this one is on, then this one's off. If this one is on, this one's off. Right? They'll go back and forth, right? And then I talked about being able to reach in and pull down to make it work. Okay. Well, that's these diodes here. See these diodes? This diode goes over to preset, and this diode goes over to clear. So you can reach in here, you can preset it, you can reach in over here, and you can clear it. So that's what those diodes do, right? Okay, great. And then we've got these transistors, which are these bottom two that I drew here, right? This transistor can pull down over here, and this transistor can pull down over here. And look, they're in a flip-flop state also. They can't be the same. They're always opposite to one another. You can either have 1, 0, or you can have 0, 1. But you can't have 0, 0, you can't have 1, 0, okay? So it's either one or the other. So if you imagine that there's an enable, then if this guy is set to 0, 1, then it'll set this guy. If this is 1, 0, then boom, it'll set that guy, right? And then there'll be an enable. Well, there's our enable, okay? There is our enable. And so we can either use this one or we can use this one. All right. Now it's going to be a little more complicated. All right, so let me draw that. Okay, so you remember that I had a teeter-totter and I had 2 transistors that are going to be our set reset transistors, right? All right, so we have these guys coming out here, right? And then we're either going to do it one way or the other way, right? So let's say we have something come in over here, and we run it through an inverter, okay? And we have this. So let's say this is, we'll call it D. How about if we call it D? Okay? So this is going to be D, and this is going to be not D, okay? D and not D. And we're going to bring this one around, tie it here. We're going to bring this around, we're going to tie it here. So now, if D is a 0, then this one will be off, that'll be high, this one will be on. And if D is a 1, then this transistor will be on, and this transistor will be off, right? And then if I take these two, and I put them through another transistor, then that teeter-totter will be set either to 0, 1 or 1, 0, okay? So this D can rattle up and down all at once, but as soon as I enable this thing, okay, it will take that state, okay? Whatever the state of D was, it will allow the circuit to happen, right? And guess what? That's what we've got here, right? And we have the enable is our clock pin, and the D is our D. If you see down here, can I get in a little farther, a little bit? See, D goes through this transistor, and it comes out with this, and then it goes through a second transistor, and it comes out over here. So this is going to be the D and the not D, right? One's going to be the opposite of the other. And there's these little diodes here that allow you to pull down. So our D comes in, we're going to have 0, 1 or 1, 0, and then whenever the clock goes, boom, this thing will latch, okay? And what does it mean to be edge triggered? What does it mean that this circuit only operates on positive edges? Isn't this a state machine? Isn't this, if clock is high, then this thing always works? Well, this set reset flip-flop will take the state of D, but it won't change. No matter if you enable it, or you stop enabling it, or you enable it again, once this flip-flop is set, it's set, okay? And so once it gets set, it doesn't matter how many times you see an edge here, okay? I should actually say no matter how often you see a high state here, the rest of the circuit won't do anything, okay? So what does it mean to be edge triggered? It really doesn't. It's actually level sensitive, right? This base has to be high for the circuit to operate. So it's a level circuit. But it doesn't matter if that state goes high. So if you take a look at a truth diagram, let's say you have 0 and suddenly you get a 1 and this flip-flop will set, and then you get a 0, 0, 0. It doesn't matter. If you keep putting zeros in this thing, it won't do anything. And if you just continue to hold it high, if you have high, 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 it won't change anything over there. It's only when you change the state of D and you have this rising edge again, okay? It's the only time it will fire again. So I found it very interesting that, is it edge triggered? Is it a correct terminology to call it edge, or is it a correct terminology to call it a high state with bounce, anti-bounce, or anyway, it is funny. It is funny to go look at this and say, yeah, okay, it's a positive edge. That just means that it went high. Not that it's actually looking at an edge. It's just looking at a high state. And so, yeah, it's very, very interesting. And it'll trigger somewhere along that edge, depending on the, base emitter junction here, and this diode and stuff. There'll be some level at which it will switch, but then it just won't switch anymore. Once it goes high, it's high. So yeah, I found that very, very interesting. Okay, so the other question he had was, how does a microprocessor be edge triggered? Okay. And I've kind of covered this before, but I didn't really talk about it too much. So let's say you have a microprocessor and it's looking at a particular line. Okay, so here's the microprocessor, microcontroller, whatever it is over here, right? And here's a D4. Okay, so you got some line coming into D4. Now the software can go read this data port, and it can go check once in a while. It can have a program where it's going in this loop, and right here is a read instruction, and that read instruction will look at the value of D4, and it'll go in this loop. This is called a round robin or a polling. You'll hear it called different names, but it's basically just going around and around and around, waiting for this line to go high. Now, people would say, this is not edge triggered, this is level triggered. It's whenever the level of D4 changes, will the microprocessor finally see it. Okay, so this is a level thing. So is there a way to have one of these little guys here on a microprocessor? Okay, now on a microprocessor, they don't draw them this way. They call them interrupts. Interrupts, okay? And what an interrupt is, it has a circuit like this in the microprocessor, and it's looking for edges. And when it sees a rising edge, it says, oh, I saw a rising edge. And there's hardware in the microprocessor that says, there was an interrupt that occurred. What does that mean? Well, it says the hardware is going to interrupt whatever you're doing. It's going to say, hey, I know you're running this little program over here, but I'm going to say, whoa, wait a minute, we're going to do something different for a while. And it creates an interrupt. And these are, they can be either level sensitive or edge sensitive, okay, depending on the microprocessor. You could also have a Schmidt trigger here, okay, like a 7414 Schmidt trigger. This is an edge trigger device, and you could run that into here. Or you could put in your 7474 and put that into here if this is level sensitive and not edge sensitive. Okay, so you can make it edge sensitive on the outside and then make this go high and stay high. All right, so in an interrupt, when an interrupt occurs, there's hardware in the microprocessor that says, we're going to do something different. We're going to go down over here and we're going to look, and usually there'll be like an address, okay? and there's an interrupt address. When this pin gets pulled, it says, okay, jump to this address and do whatever is there. And it will go to this address, it'll execute some code, and when you're ready to be done, you can do a return or some other command that basically turns off the interrupt, says, okay, I'm done with my interrupt, I can go back to what I was doing. So you might be doing this, suddenly get an interrupt, you go do this, and then when you come back, you take off where you left off, okay? There's stack pointers and there's other things, but that's what that does. You can turn these guys on by doing an enable interrupt, okay? And you can turn them off by a disable interrupt. There'll be commands in the microprocessor. So if you never want to be interrupted, it's like taking your phone off the hook. You can say disable interrupts, so you'll never allow this to happen. And then you can say enable interrupts. A lot of times you don't want to get an interrupt on top of an interrupt. And so when you interrupt, you come down here. The very first thing you do is you disable interrupts, okay? Because you don't want this to get interrupted by somebody else. And so you get an interrupt, you go execute this, and the very, very last thing before you return, you enable interrupts, not enable interrupts, and go back to what you were doing. So anyway, I know that was a very long and kind of roundabout way, but it just says that, what does it mean to be edge triggered? Well, it's not technically an edge. It's just a high level that you deal with it a different way. Okay, so what do you think? Do we call it an edge? Do we call it, so we call it edge. Do we call it a transition? Transition, I don't know if I can spell these out. Transition, or do we call it a state change? Okay? So, which is more appropriate, or is it just kind of what we keep in our head? Are we thinking about edges? Are we thinking about transitions? Are we thinking about a change in state? Does it matter? I don't know. What do you think? I've always thought it was edges, and I kind of think of it that way. But if you look at the circuits, is it really an edge, or is it just a state change? And I don't know.